A very good morning, my dear students. In the previous lecture, we are discussing about the sequential logic circuits, and in that sequential logic circuits, we have started discussing sequential logic circuits, starting with different types of flip flops like RS flip flop, JK flip flop, D flip flop, delay flip flop, and toggle flip flops. And after the discussion of flip flops, we have mainly concentrated on discussing the different types of shift registers like shift left register, shift right register, and there are different ways of different types of shift registers. They are serial in, serial out shift register, serial in, parallel out shift register, parallel in, serial out shift register, and then parallel in, parallel out shift registers. So these are the things we have seen in the previous lectures. In that completes, I think, the fifth chapter. Fifth chapter mainly deals with the sequential logic circuit basics, that is discussion of all the flip flops and also the different types of shift registers. So that completes the fifth chapter. Now we will move on to the discussion of sixth chapter, which involves mainly other topics of sequential logic circuits. They are different types of counters and also memories, different types of memories like RAM, ROM, classification of memories, okay, explanation of different types of memories. All those things will be discussed in the sixth chapter. So in this sixth chapter we will mainly uh, start the discussion of sixth chapter with the types of counters in this lecture. So in this lecture we will start discussing the types of counters, and one of the type of counter is ripple counter. That also we will see the working of ripple counter and all those things. So the main objective of this lecture is to know what is a counter and what are the different types of counters, and difference between synchronous and asynchronous counters, and also we will see the working of uh, ripple counter. Ripple counter is the example of asynchronous counter. So we will see in this lecture all these things. The What is the definition of a counter, what are the different types of counters, what is the differences between synchronous and asynchronous counters, and also the one of the type of asynchronous counter which is called as ripple counter. We will see the working of that ripple counter. Firstly, what is a counter? Counter is nothing but a register which has the capability of counting the number of clock pulses that have applied at the input, at the clock input of any register circuit or flip flop. Okay, so counter is not much differing with respect to the register. Counter is nothing but a register which has the capability of counting the number of clock pulses that you are applying at the input clock. Okay, so for each and every register, that means for each and every flip flop available in that register, you are applying the clock pulses. So the counter will be having the extra feature when compared with the register, like it will be counting the number of clock pulses that you are applying to each and every flip flop available in that particular register. That is the main definition of counter. As the name itself tells, counter. Counter means it is counting something, and it is counting the number of clock pulses that are applied at the input clock. Okay. So flip flops connected together to perform counting operation. Like I said, registers are also combination of flip flops. Even these counters are also combination of flip flops. So interconnection between the flip flops will give you the operation of counter and counting operations. And gates in a counter are connected to produce prescribed sequence of binary states in register. For example, if you want to produce some fixed output, fixed pattern, let us say I am considering four flip-flops so that you can able to produce 4-bit output like this. Let us say 0000, 0001, 0010, 0011, 0100, 0101, and so on up to we'll be having 4 1. So total 16 combinations you will be getting by considering 4 flip-flops, by considering 4 flip-flops, and these are the different 16 output states. These are the 16 different output states. For example, if I want to count only up to here, that means I want to count only these output states, that means 0 0 0 0, 0 0 0 1, 0 0 1 0, 0 0 1 1, and then 0 1 0 0. So only 5 output states I need to count, and remaining all the output states I need to omit. Okay, so you can neglect the remaining output states. That means I want to design a circuit which will be counting only these 5 output states, so that I can call that counter as mod 5 counter. I can call that counter as mod 5 counter. So mod 5 counter, in the sense 5 represents the number of output states, 5 represents the number of different output states, number of different output states. Okay, so gates are used in a counter to produce prescribed sequence of binary output states in a register. Okay, and if you are considering n number of flip-flops in a counter, it may count a maximum of up to 2 to the power of n number of clock pulses. So for a given n flip-flops, which will be counting a maximum number of 2 to the power of n number of clock pulses. Okay, so for a given n number of flip-flops in a counter or register, it can count a maximum of how many number of clock pulses? 2 to the power of n number of clock pulses. So for counting 5 clock pulses, let us say, for counting 5 clock pulses, how many number of flip-flops are required? That means 2 to the power of n is equal to 5, and what is the minimum value of n here? N should be equal to 3, because if n is equal to 2, 2 to the power of n becomes 4, which is less than 5. So that's why for counting 5 number of clock pulses, the minimum number of flip-flops required is 3. Okay, so that means I can say for designing mod 5, we will see what is this mod and all those things in the next slide. For designing mod 5 counter, you need minimum of 3 flip-flops. Mod 5, in the sense, number of clock pulses or number of different output states available should be equal to 5. So for constructing mod 5 counter, you need a minimum of 3 flip-flops. But by using 3 flip-flop, what are the maximum number of output states it can count? 8, because 2 to the power of 3 will be equal to 8. Are you understanding? So this is nothing but modulus of a counter. So for n number of flip-flops used in the counter, that counter can be counting the number of clock pulses up to a maximum of 2 to the power of number of flip-flops. So 2 to the power of number of flip-flops will be the maximum number of clock pulses that can be counted by a n flip-flop counter. Okay. Next we will see what is the definition of modulus of a counter. In short form, you can call it as mod. Mod. Okay, so modulus is defined as the number of states that a counter can count, number of different output states that a counter can produce is called modulus of a counter. So n number of flip-flops may count clock pulses up to maximum of 2 to the power of n. Examples you can consider: mod 3 counter, mod 5 counter, mod 16 counter, mod 10 counter, etc. Okay, if you observe this first one, mod 3 counter, for realizing this mod 3 counter, that means 2 to the power of n is equal to 3 here. That means what should be the minimum value of n? N should be equal to 2. Then only you can able to realize this 2 to the power of n is equal to 3 counter. Okay, so for realizing mod 3 counter, number of flip-flops required will be 2. Similarly, for realizing mod 5 counter, number of flip-flops required will be equal to 3. Just now we have seen. Okay, so for realizing mod 5 counter, the number of flip-flops required will be 3. And for realizing mod 16 counter, number of flip-flops required will be 4, because 2 to the power of 4 will give you 16 different output states. So for realizing mod 16 counter, you need 4 number of flip-flops. You need 4 number of flip-flops. Similarly, in a similar manner, for constructing mod 10 counter, what should be the value of n? That is, how many number of flip-flops are required? Again, will be equal to 4, because by using 3 flip-flops, you can count maximum of 8 clock pulses. That means up to mod 8 counter, n is equal to 3. But if you are considering greater than 8, that is mod 9 or mod 10 counter, the minimum number of flip-flops required should be 4. But by using 4 flip-flops, what are the maximum number of uh, clock pulses counted? It will be 16. So from mod 9 to mod 16, you can have 4 flip-flops. From mod 9 to mod 16, for constructing from mod 9 to mod 16 counters, mod 9 or mod 10, mod 11, 12, 13, 14, 15, 16. So up to mod 9, from mod 9 to mod 16 counters, you need 4 flip-flops. Similarly, from mod 5 to mod 8, you need 3 flip-flops. From mod 5 to mod 8, you need 3 flip-flops. So for the construction of mod 5 to mod 8 counters, you need 3 flip-flops, whether it is mod 5, mod 6, mod 7 or mod 8. So for all the 4 different types of counters, you can have 3 number of flip-flops. Similarly, from for mod 3 and mod 4, for mod 3 and mod 4 counters, you need 2 number of flip-flops. You need 2 number of flip-flops. Okay, so that is nothing but modulus of a counter. So n number of flip-flops may count clock pulses up to 2 to the power of, up to maximum of 2 to the power of n number of clock pulses. So examples of modulus of a counter is mod 3, where in mod 3 counter the number of output states is 3. It can count 3 clock pulses. Similarly, mod 5 means number of output states is 5 and 5 clock pulses are required. And mod 16 means number of clock pulses are 16 and 16 different outputs will be getting. And mod 10 means number of output states will be 10. Okay. So this is something about modulus of a counter. Next we will see the different types of counters. According to the way they are clocked, counters are classified as asynchronous counters and synchronous counters. Okay. How you are applying the clock to the counter circuit, depending upon according to the way you are applying the clock. According to the way you are applying the clock to the counter circuit, the counters are classified into 2 categories. The counters are classified into 2 categories. First one is asynchronous counters. Second one is synchronous counters. The best example for asynchronous counters is ripple counter, and the example for synchronous counters is ring counter. Example for synchronous counters will be ring counter. So depending upon how you are applying the clock input to the counter circuit, depending upon the way you are applying the input to the input to the counter circuit, the counters are classified into 2 categories. First one is asynchronous counters and second one is synchronous counters. The example for asynchronous counters is ripple counter, and the example for synchronous counters will be ring counters. Example for synchronous counters will be ring counters. Okay, and in the case of asynchronous counters, clock input is applied only to the first flip-flop, and the clock input for the subsequent flip-flops will be derived from the outputs of previous flip-flops. Okay, that is the concept involved in asynchronous counter. That means the clock input for all the flip-flop is not synchronous, is not same. You are not applying the clock input to all the flip-flops at a time. You are not applying the clock input to all the flip-flops at a time. That is the meaning of asynchronous counters. Whereas in the case of synchronous counters, you are applying the clock input to all the flip-flops at a time. same clock is applied to all the flip-flops at a time. That is the meaning of synchronous counters. In the case of asynchronous counters, uh, clock input will be applied only to the first flip-flop, and the clock input for the rest of the flip-flops will be derived from the outputs of previous flip-flops. That is the concept involved in the asynchronous counters. And in the case of synchronous counters, clock input is applied to all the flip-flops at a time. That is the meaning of synchronous counters. So these are the different types of counters based on how you are applying the clock input to the counter circuits. Next, coming to the asynchronous and synchronous counter differences. In the case of asynchronous counter, first flip-flop is clocked by external clock pulse, and the subsequent flip-flops are clocked by the Q or Q bar output of the previous flip-flops. As I told earlier, asynchronous counter is nothing but clock input is not applied simultaneously to all the flip-flops at a time. That means first flip-flop will be applied the clock input externally, and the subsequent flip-flops will be applied with the clock input based on the Q or Q bar output of the previous flip-flop. That means the output of first flip-flop is given as clock input to the next flip-flop, and so on, depending upon the number of flip-flops you are using in that asynchronous counter. In contrary to that, in the case of synchronous counters, clock input is applied to all the flip-flops simultaneously. Clock input is applied to all the flip-flops simultaneously and at a time. So same clock pulse is applied to all the flip-flops at a time. That is the meaning of synchronous counters. In the case of asynchronous counters, only first flip-flop is applied with external clock input, and the clock input for the rest of the flip-flops will be derived from the outputs of previous flip-flops. Will be derived from the outputs of previous flip-flops. Similar, and in the case of synchronous counters, clock input is applied to all the flip-flops at a time simultaneously. That is the basic difference between asynchronous counter and synchronous counters. And when compared to the speed of the counters, asynchronous counters are slow. Asynchronous counters are slow when compared to the synchronous counters, and synchronous counters are faster when compared with the asynchronous counter, because since clock input is not applied to all the flip-flops at a time, it will be taking some time to produce the required output. It is taking some time to reproduce the required output. That's why asynchronous counter is slow in nature compared to the synchronous counter. Whereas in synchronous counter, since clock input is applied to all the flip-flops at a time simultaneously, output will be available after one single clock pulse itself. That's why synchronous counters are faster compared to the asynchronous counters. And if you observe, synchronous counters are nothing but serial counters, and asynchronous counters are nothing but parallel counters. Serial counters means what? You will be taking the output only at one instant of time. Okay, and in the case of parallel counters, uh, all the outputs are available parallelly at a time. Whereas in the case of serial counters, for getting 4-bit output, you need 4 clock pulses, and for getting 4-bit output in the case of synchronous counter, you need only 1 clock pulse. That is the difference between serial counter and parallel counter. So asynchronous counters will be called as serial counters, and synchronous counters will be called as parallel counters. And one more difference is asynchronous counters. In asynchronous counters, the propagation delay is more. In asynchronous counters, the propagation delay is more, and in the case of synchronous counters, propagation delay is less. So these are some of the basic differences between asynchronous counters and synchronous counters. Okay, I repeat once again. In the case of asynchronous counter, only first flip-flop is applied with external clock pulse, and the clock input for the rest of the flip-flops will be derived from the outputs of previous flip-flops. That is the concept involved in asynchronous counter. And in the case of synchronous counter, clock input is applied to all the flip-flops at a time simultaneously. And in the case of synchronous counter, clock input is applied to all the flip-flops at a time simultaneously. Asynchronous counters are slow compared to the synchronous counters, and synchronous counters are faster compared to the asynchronous counters. And similarly, asynchronous counters are called serial counters, and synchronous counters are called parallel counters. And in the case of asynchronous counters, cumulative propagation delay is more, And in the case of synchronous counters, propagation delay is less. So these are some of the differences between asynchronous and synchronous counters. Next we will move on to the discussion of the ripple counter, which will be coming into the category of asynchronous counters. Okay, and if you observe the asynchronous counter, uh, I'll be discussing the operation of this. I'll be discussing the operation of this asynchronous counter, which will be consisting of 4 flip-flops as shown. Okay, so now I am using the four types of 4 JK flip-flops I am using. First flip-flop is FF0, FF1, FF2 and FF3, and FF0 happens to be LSB and FF3 happens to be MSB. Okay, so by using 4 flip-flops in a ripple counter circuit, it can able to count a maximum of how much? 2 to the power of 4, which is equal to 16 clock pulses. It can able to count. It can able to count 16 number of clock pulses. Maximum of 16 number of clock pulses it can able to count. Okay, so for the construction of ripple counter, I am using JK flip-flops, 4 JK flip-flops, in which the inputs J and K inputs to all the flip-flops are applied to VCC, are tied to VCC. That means J0 is equal to K0 is equal to 1. Similarly, J1 is equal to K1 is equal to 1. Similarly, J2 is equal to K2 is equal to 1. And similarly, J3 is equal to K3 is equal to 1. That means all the J and K inputs of each and every flip-flop are connected to VCC or logic high. Okay, so whenever I am giving J is equal to 1 and K is equal to 1 to all the JK flip-flops, that means JK flip-flop is operated in toggle mode. JK flip-flop is operated in toggle mode. What do you mean by toggle mode? So whenever J is equal to 1 and K is equal to 1, then present output will be equal to complement of the previous output. Present output will be equal to complement of the previous output. So for J is equal to 1 and K is equal to 1, the output of JK flip-flop Qn plus 1 will be equal to Qn bar. Qn plus 1 will be equal to Qn bar. That means whenever J is equal to 1 and K is equal to 1, the output of JK flip-flop will be toggled. The output of JK flip-flop will be toggled. What do you mean by toggling of the output? If the previous output is 0, present output becomes 1. If the previous output is 1, present output becomes 0. That is the meaning of toggling the output. Okay, so that means Qn plus 1 is equal to Qn bar. Present output is equal to complement of the previous output. Present output is equal to complement of the previous output. So that is the operation of JK flip-flop, and this operation will be valid for all the flip-flops, for 4 flip-flops which are used in the construction of ripple counter. And this is something about JK and inputs of the JK flip-flop, and also depending on the input how the output is responding. And similarly, if you observe the clock input for each and every flip-flop, for FF0 clock input or external clock pulse is applied. For only FF0, for the first flip-flop, only external clock pulses are applied, and for the clock input for the next flip-flop, clock input for the next flip-flops will be derived from the output of the previous flip-flop, will be derived from the output of the previous flip-flop. So whatever the output that is generated at the output of FF0, that will be given as in clock input for the next flip-flop. Similarly, whatever the output that is generated from FF1, that is Q1, that is given as clock input for the next subsequent flip-flop, that is FF2. And similarly, whatever the output that is generated at FF2 output, that is Q2, that is given as clock input to the FF3 flip-flop. So this is nothing but asynchronous counter. This is nothing but asynchronous counter. You are not applying the same clock pulse to all the flip-flops at a time simultaneously. You are not applying the same clock pulse to all the flip-flops at a time simultaneously. Instead, only first flip-flop is applied with the external clock pulse, and the clock input for the rest of the flip-flops will be derived from the outputs of the previous flip-flops. Will be derived from the outputs of the previous flip-flops like this. So Q0 output is given as clock input to the FF1 flip-flop. Similarly, Q1 output is given as clock input for the FF2 flip-flop. Similarly, Q2 output is given as clock input for the FF3 flip-flop. So this is the type of clocking that is asynchronous. Asynchronously, you are applying the clock input to the flip-flop. So asynchronous counter consisting of 4 flip-flops is the figure shown. So FF0 is LSB and FF3 is MSB. So whenever clock pulse is applied, the output of FF0 will be changing continuously. So if you are applying first clock pulse, output will be changing. Let us say previous output is 0, then present output becomes 1. Similarly, whenever clock pulse is again, second clock pulse is applied, again Q0 becomes 0 from 1 to 0. So likewise, Q0 toggles for each and every clock pulse. Q0 toggles for each and every clock pulse, whereas Q1, Q2, Q3 will be toggling less often compared to the FF0 output. So FF1, FF2, FF3 outputs will be changing only when the clock pulse is changing its state from high to low. Whenever you are considering negative edge triggering, whenever you are considering negative edge triggering clock pulse, that means whenever the clock is changing its state from logic high to logic 0, whenever the clock is changing its state from logic high to logic 0, at that instant of time, let us say the outputs of the flip-flops will be changing depending upon the J and K inputs. Depending upon the, since J and K inputs are always equal to 1, whenever clock input is changing from 1 to 0, that is negative edge triggering, at that negative edge triggering only, the output of the JK flip-flop will be toggle. The output of the JK flip-flop will be toggle. Toggling means the present output becomes complement of the previous output. Present output becomes complement of the previous output. If you observe the construction details, clock pulses to be counted are applied to the clock input of first flip-flop. Clock pulses to be counted are applied to the clock input of first flip-flop, and the output of each flip-flop is connected to the clock input of the next higher flip-flop. As we have discussed in the previous slide, the output of each flip-flop is connected to the clock input of the next higher flip-flop. Like FF0 output is connected to the clock input of FF1. Similarly, FF1 output is connected to the clock input of FF2. Similarly, FF2 output is connected to the clock input of FF3, and so on. So for all stages of J and K are tied to the supply voltage, that is J is equal to K is equal to 1, which acts as T flip flop. T stands for toggle. So whenever J is equal to K is equal to 1, the JK flip flop will be in toggling mode. Toggling mode stands for present output will be equal to complement of the previous output. So the principle of operation is like this: each flip-flop will toggle when its clock input receives a negative edge. Since I am applying negative edge triggering clock pulse to all the flip-flops, clock input to all the flip-flops, so whenever the flip-flops, whenever any flip-flop receives negative going edge of the clock, at that instant of time, the output will be toggled. So initially, let us assume Q is equal to Q3, Q2, Q1, Q0, and initial output word is Q is equal to 0, 0, 0, 0. So initially, all the flip-flops are cleared. Initially, all the flip-flops are resetted or cleared. What do you mean by flip-flops are resetted or cleared? Making the output of all the flip-flops to be equal to 0, irrespective of the input values, and also irrespective of the clock. So initially all the outputs of flip-flops are cleared. That means all the outputs Q3, Q2, Q1, Q0 is equal to all zeros. So Q0 toggles for each negative clock edge since it receives each clock pulse. So for each and every clock pulse applied to the first flip-flop, the Q0 output, which is nothing but the output of first flip-flop, that is FF0, will be toggling for each and every negative clock edge, and the remaining flip-flops toggles less often. So these are the states of asynchronous counters. Initially, whenever no clock pulses are applied, initially I am assuming 0, 0, 0, 0. are the outputs, and whenever the first clock pulse is applied, the output of first flip flop, that is Q0, will be toggled. So previously it is 0, now it is becoming 1. Okay, so whenever the Q1 output will be changing, only when Q0 is changing its state from 1 to 0. That is nothing but negative edge triggering. So whenever Q0 is having the transition from 1 to 0, whenever the Q0 value changes from 1 to 0, at that instant of time, the Q1 output toggles. Because why it is like that? Because Q0 output is given as clock input to the next flip flop. Q0 output is given as clock input to the next subsequent flip flop, that is FF1, for which the output is Q1. So Q1 toggles only when Q0 output is changing its state from 1 to 0 only. That is nothing but negative going edge triggering. So whenever Q0 output is changing its state from 1 to 0, then only Q1 toggles. So for 0 1 there is no toggling. Okay, only for 1 0 only will toggle. So 1 to 0 it is happening like that. Okay, so since Q0 is changing from 1 to 0, Q1 is changing from 0 to 1. Similarly 1 to 0, 1 to 0. Similarly 1 to 0, 0 to 1. Likewise, whenever Q0 output is changing its state from 1 to 0, logic 1 to logic 0, that is nothing but negative edge triggering clock. So whenever Q0 is changing its state from 1 to 0, then only the second flip flop, that is FF1, will be toggled. And similarly, whenever Q2 is changing its state from logic 1 to logic 0, then only Q3 whenever Q1 is changing its state from logic 1 to logic 0, then only Q2 toggles. If you observe, whenever Q1 is changing its state from logic 1 to logic 0, then only Q2 toggles. Logic 1 to logic 0, then only Q2 toggles. Logic 1 to logic 0, then only Q2 toggles. Logic 1 to logic 0, then only Q2 toggles. Okay, so whenever Q1 is changing its state from logic 1 to logic 0, that means negative edge triggering again, which is nothing but the clock input for the Q2 flip flop, clock input for the FF2 flip flop. So whenever Q1 is changing its state from logic 1 to logic 0, then the Q2 toggles. Okay, similarly, whenever Q2 is changing its state from logic 1 to logic 0, then only Q3 toggles. So only whenever Q2 is changing its state from logic 1 to logic 0, here Q2 is changing its state from logic 1 to logic 0, then only Q3 toggles. Whenever Q2 is changing its state from logic 1 to logic 0, then only Q3 toggles. Okay, so likewise, if you observe the operation, all the 16 combinations are covered starting from 0 to 15. So all zeros to all ones, and after all ones, again the 16th state becomes again all zeros. It will come to initial state. It starts counting again. As long as you are applying the number of clock pulses to the counter circuit, it keeps on counting. Okay, so starting from all zeros to all ones, and even after all ones, even after getting output of all the flip flops as all ones, if you are applying clock pulses again, what will happen? It counts again. The process of counting the number of clock pulses is repeated as long as you are applying the clock pulses to the counter circuit. So this is the truth table of the ripple counter. So these are the number of clock pulses which you are applying at the input of first flip flop, at the clock input of first flip flop, and these are the different output states of each and every flip flop. Q3 is the output of last flip flop, Q2 is the output of FF2, and Q1 is the output of FF1, and Q0 is the output of FF0. If you observe, for each and every clock pulse, the Q0 output toggles, because this is the flip flop which will be receiving the external clock pulse. This is the flip flop which will be receiving the external clock pulse. So for the application of each and every clock pulse to the Q0 flip flop, to the FF0 flip flop, its output toggles always. Its output toggles always. Okay, so this is something known as, you can also call this truth table as state diagram. Truth table also called as state diagram for ripple counter. State diagram for ripple counter. Now counting sequence is as follows. First it will be 0 0 0 0. Next Q0 output toggles. Q0 output toggles like this, 0 to 1. Next 0 0 1 0, 0 0 1 1, 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 triple 1. Next 1 triple 0, 1 0 0 1, 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, lastly 1 1 1 1, and then again it come back to the initial state, that is 0 0 0. So it is a cyclic process. As long as you are applying the clock pulses continuously, the counter keeps on counting the number of clock pulses like this. Okay, so this is the counting sequence of the ripple counter, 4-bit ripple counter. So since you are using 4-bit ripple counter, it can able to count a maximum of how many clock pulses? 16 clock pulses. It can able to count a maximum of 16 clock pulses, and starting from output states from all zeros to all ones, starting from output states of, starting from 4 zeros to 4 ones. So these are the 16 different output states you will be getting for a 4-bit ripple counter or 4-bit asynchronous counter. Next, if you observe, the Q0 changes state at the falling edge of the each pulse, and all other Qs, all other outputs change when the output of preceding flip flop changes from 1 to 0. If you observe, Q0 changes, and whenever Q0 is changing from 1 to 0, whenever Q0 is changing from 1 to 0, then only Q1 toggles. Then only Q1 toggles. Similarly, whenever Q1 changes its output state from 1 to 0, whenever Q1 changes its output state from 1 to 0, then only next flip flop will be toggled. That means Q2 toggles. Then only Q2 toggles. Toggles means present output will be equal to complement of the previous output. Present output will be equal to complement of the previous output. Similarly, whenever Q2 is changing its state from logic 1 to logic 0, whenever Q2 is changing its state from logic 1 to logic 0, then Q3 toggles. Then Q3 toggles. So that is the meaning of the statement. All other outputs changes when the output of preceding flip flop changes from 1 to 0. When the output of preceding flip flops, all the outputs change when the output of preceding flip flop changes from 1 to 0, because that preceding flip flop output which is changing from 1 to 0 is given as clock input to the next subsequent flip flop. That is nothing but negative edge triggering clock. That is nothing but negative edge triggering clock. The negative transition ripples through the counter from LSB to MSB. So this is the timing diagram of asynchronous counters. Let us assume these are the clock pulses 1 2 3 4 5 6 7 8. So for each and every negative going triggering pulse, the corresponding first flip-flop output will be toggled. Initially Q0 is 0, now it is made 1 after first clock pulse. So after first clock pulse the contents will be 0 0 0 1. Okay, after second clock pulse the contents will be 0 0 1 0. Similarly after the third clock pulse contents will be 0 0 1 1. Similarly for after the fourth clock pulse 0 0 0 1 0 0. Similarly after the fifth clock pulse 0 1 0 1. Similarly after the sixth clock pulse 0 1 1 0. After seventh clock pulse 0 1 1 1. Similarly after eighth clock pulse 1 0 0 0. After ninth clock pulse 1 0 0 1. After 10th clock pulse 1 0 1 0. After 11th clock pulse 1 0 1 1. After 12th clock pulse 1 1 0 0. After 13th clock pulse 1 1 0 1. After 14th clock pulse 1 1 1 0. And after 15th clock pulse all ones you will be getting, and again after 16th again all the outputs will become zeros. It will start counting once again. So this is the timing diagram of asynchronous counter. So if you observe Q0 output toggles for each clock pulse. Q0 output toggles for each and every clock pulse, whereas Q1 output will be toggling. Q1 output will be toggling whenever Q0 changes from 1 to 0. So whenever Q0 changes from 1 to 0, then only Q1 output will be changing its state. Then only Q1 output will be changing its state. If you observe. Okay, so at this instant of times only the Q1 output will be changing. Similarly Q2 output will be changing only when Q1 output changing its state from logic 1 to logic 0. Only at 4 instant of times the Q1 or Q2 output will be changing. Similarly Q3 output will be changing only when Q2 is changing its state from logic 1 to logic 0. Okay. So this is something about the timing diagram of synchronous counter or asynchronous counter or ripple counter, 4-bit ripple counter. So since I am using 4 flip-flops, it can able to count a maximum of 16 number of clock pulses. It can able to count a maximum of 16 number of clock pulses starting from 1 to 16. So for 1 to 16, Q0 output toggles for each and every clock pulse, and Q1 output toggles only when Q0 is changing its state from logic 1 to logic 0. Logic 1 to logic 0, logic 1 to logic. Similarly, Q2 output will be changing only when Q1 output is changing from logic 0, logic 1 to 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 logic 0. Similarly, Q3 output will be changing only when Q2 output is changing from logic 1 to logic 0. Okay, so this is the timing diagram of asynchronous counter. So overall summary, if you observe, a counter is a sequential circuit that counts the clock pulses in binary form, and counters are of two types based on how you are applying the clock input to the counter circuit. So based on the how you are applying the clock input to the counter circuit, you can classify the counters into two types: asynchronous counters and synchronous counters. The examples for synchronous counters will be ring counter, and the example for asynchronous counters will be ripple counters. Okay, so example for synchronous counters will be ring counter, and example for asynchronous counters will be ripple counter. So these are the different types of counters based on how you are applying the clock input to the counter circuit. And also we have seen in synchronous counters all the flip-flops are triggered by the same clock, and in asynchronous counters like ripple counters each flip-flop is triggered by the output of the previous flip-flop. And we will move on to the quiz. A 4-bit ripple counter counts up to how many clock pulses? It will be equal to 16. Answer will be 16. Counts up to 15. See, if you see the question, a 4-bit ripple counter counts up to 15 starting from 0. So total 16. 0 to 15 in the sense it can able to count 16 clock pulses, but it will be starting from 0 to 15. So a 4-bit triple counter counts up to 15, not 16. So 15 in the sense it will be 0 to 15. So total it becomes 16. So answer will be 15 will be the answer. Next, a ripple counter is a synchronous counter, asynchronous counter, either A or B, none of the above. So the answer will be what? Asynchronous counter. So ripple counter will be always asynchronous counter, in which you are not giving the clock pulse, same clock pulse at a time to all the flip flops simultaneously. So first flip flop will be applied with external. First flip flop will be applied the clock input with the external clock pulse, and the next subsequent flip flops will be the clock input for the subsequent flip flops will be derived from the outputs of previous flip flops. That is the concept involved in asynchronous counter. So clock input is not same to all the flip flops; it is different. That's why ripple counter will be coming into the category of asynchronous counter. Next, these are the frequently asked questions. Write the differences between synchronous and asynchronous counters. If you observe, in the case of asynchronous counters, uh, for the first flip flop, clock input is applied externally, and the clock input for the subsequent flip flops, remaining flip flops, will be derived from the outputs of the previous flip flops. That is the meaning of asynchronous. And in the case of synchronous flip flops, synchronous counters, the clock input will be applied to all the flip flops at a time simultaneously. And if you observe, in the case of asynchronous counters, the clock input is different. Input to all the flip flops is different, so it will be taking more time. It is slower. Asynchronous counters are slower compared to the synchronous counters, whereas synchronous counters are faster compared to the asynchronous counters. And asynchronous counters are nothing but serial counters, whereas synchronous counters are nothing but parallel counters. And in the case of asynchronous counters, the cumulative propagation delay is more. The cumulative propagation delay is more, since clock is different to each and every flip flop. Since clock is different to each and every flip flop, the cumulative propagation delay is more in the case of asynchronous counters. And since clock is applied to all the flip flops at a time simultaneously, the propagation delay will be very less in the case of synchronous counters. So these are some of the differences between synchronous counters and asynchronous counters. And also we have seen the working of 4-bit ripple counter with block diagram, state table, and timing diagram. We have seen all these things. Block diagram, which consists of 4 flip flops, 4 JK flip flops, and the inputs to all the JK flip flops are tied to VCC, that is logic 1. And first flip flop clock input is given with the external clock input, and the clock input for the remaining flip flops will be derived from the outputs of previous flip flops. So that will be the block diagram of 4-bit ripple counter. And state table, a number of clock pulses before applying any clock pulse, that is 0. All the outputs of each and every flip flop will be 0, that is q3 is equal to 0, q2 is equal to 0, q1 is equal to 0, and also q0 is equal to 0. So after the application of first clock pulse, the q0 output will be changing. Q0 output will be toggled from 0 to 1. Remaining outputs will be 0. That means after applying the first clock pulse, the outputs of each and every flip flop will be q3 is equal to 0, q2 is equal to 0, q1 is equal to 0 and q naught is equal to 1. So like that, for application of each and every clock pulse, the outputs will be changing depending upon the clock input available at that particular flip-flop, and based on that you can write the state table, as well as you can also draw the timing diagram consisting of 16 clock pulses. So for each and every clock pulse, the output q naught will be toggles, and whenever q naught is changing its state from logic 1 to logic 0, which is nothing but clock input to the second flip flop, q1 output toggles. Similarly, when q1 output is changing from logic 1 to logic 0, then only q2 toggles, and similarly when q2 is changing its state from logic 1 to logic 0, in that case q3 toggles. So based on that, you can able to draw the timing diagram also. So this is something about the different types of counters, and also the working of 4-bit ripple counter. So this completes the today's lecture. In the next lecture, we will concentrate on discussing the ring counter, which is the example of which is nothing but the example of synchronous counter. Okay, and thank you for listening.